My name is Rahul Potera, and I work on power device development at SiC, which is a manufacturer of silicon carbide materials, devices, and power modules based in Lake Forest, California, in the United States. I'd like to begin by thanking you for this opportunity to present our work at the virtual IRPS conference in 2020. This work is titled Analysis of Transient HTRB Leakage in a Silicon Carbide Field Ring Termination, authored by myself and my colleagues at SiC, Dr. Tony Witt and Dr. Yongju Zhang. We know that power devices require edge termination structures to operate at high voltages. Silicon carbide and other wide bandgap power devices require edge terminations that are less sensitive by design to charges in passivation because they operate at higher electric fields and drop the same voltage over a narrower termination region than silicon, while using much the same passivation stack over the termination. In this work, we present, analyze, and model what to our knowledge is the first report of bimodal transient leakage in a traditional field ring termination in a silicon carbide device. We found the transient leakage mechanism, modeled it, and identified its root cause in the fabrication process. I shall first start with the problem in detail, then delve into the experiments we carried out to analyze it, go further to the models and simulations we used to understand the problem, and finally to the root cause we found for the bimodal transient leakage. I shall conclude by presenting previously reported optimized termination schemes as solutions that would make silicon carbide edge terminations less sensitive to excess charges arising from the process. Silicon carbide power devices often use traditional edge termination schemes proven in silicon, like single-zone JTE or floating field rings, as in the 1200-volt rated silicon carbide JBS diode shown in the figure here, with 22 floating rings with field oxide, nitride, and polyimide passivation, and a metal seal ring on the device periphery. Figure 2 shows reverse IV curves on the JBS diodes at different room temperature read points of the high temperature reverse bias or HTRB test at 1200 volt and 175 degrees C. Leakage current increases up to the 498-hour read point, then reduces asymptotically towards the 0-hour value by the 2009-hour read point. We examined this bimodal variation of leakage more carefully on a smaller sample set. In figure 3, where leakage current was observed at 175 degrees C and 1200 volt bias, but this time in real time, and found that the spike in leakage current was a function of the type of termination structure, types varying by number and spacing of termination rings. Termination types with lesser space between rings and consequently lower positive space charge between rings were more susceptible to spikes in leakage current. We then experimented with variations in bias voltage and found, as shown in figure 4, that while the magnitude of spike in leakage current reduces with bias voltage, the spike is present down to 600 volt reverse bias for the 1200 volt device. We also deprocessed the device and carried out light emission experiments in reverse bias. Figure 6 shows that this excess leakage current is correlated with light emission in the termination region, while magnitude of leakage current also correlating with intensity of emitted light. Figure 5 shows a transient leakage on 3 JBS diodes as HTRB concludes and temperature falls under bias, with excess leakage first reducing and then increasing, which indicates at least a second-order dependence of current on time and hence temperature. Although we found evidence correlating leakage with emission signature at the termination, since these JBS diodes do also leak across the Schottky contact in the active area, we wanted to rule out any impact of the active area on the excess transient leakage current we observe. At 1200 volt and 175 degrees C, active area leakage on large area devices is about 100 microamp, well below the many milliamps of leakage we observed in HTRB on these devices, as we showed in figure 3. As control cases, we tested pure PN diodes which have active area leakage less than 1 microamp, but which share the same termination structure, and found that the PN diodes exhibit the same transient leakage current spikes in HTRB as the JBS diodes of same area, providing conclusive evidence that the spike in leakage current owes its origin to the termination region. With experimental evidence pointing to the termination region as the source of this transient leakage current, we considered two models that might explain it. The first model involves field inversion. Consider impurity atoms in the passivation above the silicon carbide termination and consider that they are ionized, for example, water molecules ionized into H+ and OH- ions with different masses. When high voltage is applied at the cathode, the periphery of the device rises to cathode potential and a lateral electric field is set up in the termination region pointing from right to left in the figure. Lighter H+ ions migrate quickly down the potential gradient to the anode, whereas heavier and more sluggish OH- ions are slower in moving up the gradient to the device periphery. This differential charge motion creates a transient negative charge over the passivation, the magnitude of which increases and then decreases to zero. This negative sheet charge, if sufficient in magnitude, can invert the N- silicon carbide surface between P+ implanted rings and create a P channel to conduct current between cathode and anode. The conductivity of the P channel is modulated by concentration of negative sheet charge, and hence the leakage current first increases and then decreases. To test this model, we fabricated devices with an additional N++ seal ring, which was doped high enough not to be inverted even with electric field as high as critical field of silicon carbide, and placed this N++ seal ring outside the outermost ring of the termination region. And we found that the leakage spike in HTRB persisted to a similar extent as before. The field inversion model was thus falsified. The second model also postulates ionizable impurities in the passivation, with positive and negative ions having different mobilities, consequently creating a transient negative sheet charge over the termination region. However, in the second model, the transient negative charge is not high enough to invert N- silicon carbide, although it is still high enough to enhance local field ionization in silicon carbide in regions where the electric field is already moderately high in reverse bias. Once carriers are generated by field ionization, there is excess current but no avalanche breakdown. This is because the electric field in the passivation is not very high, and also because holes generated at the highest field regions in silicon carbide could be injected into the passivation region that lies down the potential gradient from them in this direction, thus balancing the negative charge there and providing negative feedback to the field ionization mechanism. To take this qualitative argument further in Model 2, we carried out edge-termination simulations with different magnitudes of positive and negative sheet charges in the passivation and found that with negative 5e12 per centimeter square of charge in the termination, electric field is pushed out to the outer termination rings and breakdown can start occurring as low as 800 volts, which correlates with the experimental data showed before on HTRB leakage and light emission. The ideal breakdown voltage of this structure is 1962 volts. This simulation result adds quantitative evidence to the second model, where transient variation of excess negative charge in the termination causes low levels of field ionization in high field regions of silicon carbide and increases leakage current without avalanche breakdown. This simulation also explains our observation in Figure 2 that termination structures with less positive space charge between implanted rings are susceptible to higher magnitudes of spikes, because having less positive space charge in terminations also pushes electric fields towards the outer rings, as in this simulation. With our model pointing to excess charge in the passivation region, we examined the fabrication process and zeroed in on a plasma process which created a secondary alignment mark for metal edge. Eliminating this process by changing the alignment scheme also eliminated the transient bipolar leakage, validating our model. However, there is always some charge in passivation layers, and as much as the process strives to reduce excess charges, the design, on the other hand, should strive to reduce sensitivity to these charges. Devices in wide bandgap materials like silicon carbide have higher fields in edge termination, and so need termination designs less sensitive to process variations like excess charge on termination ring spacing width. Our report of the first bimodal transient variation of HTRB leakage current in silicon carbide is further evidence in favor of using advanced edge termination schemes like silicon carbide, like guard ring assisted reserve, which was proposed by Kinoshita and colleagues in ISPST 2002. These schemes are less sensitive to process variations. Subsequently, many variations of such termination schemes that combine JTE and floating rings have been demonstrated in silicon carbide, including multiple field zone JTE, space modulated JTE, hybrid JTE, and others that we have referenced in our paper. With that, I would like to conclude this presentation of our work. I am grateful for your time and welcome your feedback on our work and on my presentation. I'll also take this opportunity to thank Professor Jim Cooper of Purdue University for enlightening discussions while we worked on this, and Dr. Kiran Chatty of the IRPS Wideband Committee for mentoring our paper and poster. Please contact me at my email address pvrahul@ieee.org. Enjoy the rest of the conference, and I look forward to hearing from many of you. Thank you.